So the started recording, right?
You can start, yes.
Yeah, it's already started.
Already started,
Uh,
okay.
Jobin, can you confirm?
Yeah, Sunil, it is recording. Recording is in progress now.
Okay,
Oh,
let's
okay.
go ahead. Then I can just stop my video just to avoid
Yeah.
any.
Okay.
Okay, so perfect. So we discussed yesterday about LC oscillator, and also we discussed about the energies involved. And I told you that if we have maybe just quick revision, uh, that if we have only a simple LC oscillator, then in this situation, because this energy will be going to be parabolic completely. So in this situation, you can see that energy levels, okay, they are going to be equally spaced. And I have written this Hamiltonian like Q square by 2C plus phi square upon 2L and equal to E psi. And this was also written in the form of differential equation. Just we are doing a quick recap so that we can start from where we left. And if you calculate the energy in this case, just give me 1 minute. Yeah. So if we calculate the energy in this case, so energy is simply comes out to be a n plus half h cut omega, and where this is L and C, and or omega naught, which we call as the 1 by LC. And in this case, all these energies levels are equally spaced. And I also tried to write down in some other form. So I defined one term which I will be using frequently. This is called the single electron charging energy. And this I define as a E square by 2C. And then I define that, let us say, if n is the number of Cooper pairs, maybe here I can make it capital N just to avoid the confusion, number of Cooper pairs, then this n will be equal to Q by 2E. So this is what we discussed yesterday already. And in that sense, this energy, which is called UC, and this energy called UL, and this is equal to total E. So this UC then comes out to be 4 times EC into N square. Then I said that what we need, and yes, also I think we said that this Josephson junction we need to introduce. So in order to create an harmonicity in the energy spacing. But I think there's another form also before going into that. So I said that the one is the phi, and this is equal to phi naught into phi. So where this phi naught is called flux quantum or reduce flux quantum, and that phi is called superconducting phase. So in that sense, when you calculate all these terms, so even UL comes out to be a 1/2 time EL phi square. And I define this EL as phi naught square upon L, and I call this as the inductive energy. So you have one term is called EC and one term is called EL. So EL is called the charging energy, you can simply say, and this is called the inductive energy. And in that sense, then H cap, I better to write in the format minus 4 EC and del square by del phi square plus U phi. So in terms of phase, so this is another equation which you need to understand. So these were the terms we used in the last class. And then I said that we need to, if you want to create a n-harmonicity, then we have to introduce Josephson junction. And this Josephson junction, I said it is going to act like a capacitor with the capacitance value of K F naught A by D. And this is also going to act like a inductance with the inductance value Lj. And this was equal to H upon 2E I naught into cos phi, which I call as the Lj naught upon I naught. So this one is called the inductance of Josephson junction. So in principle, this whole structure is going to act like a one. Symbolically, I'm going to represent in this format. So this is the capacitance called Cj, and this is symbol we use. I mean, in principle, I can represent a single symbol as well, or you can even say like inductance and capacitance. So inductance is Lj and capacitance is a Cj. So everything is already written to us. And this Lj, another form. This Lj, another form I mentioned you yesterday, this Lj also written like a phi naught phi dash and I naught cos phi. Then because of this inductance, we can calculate the potential energy of Josephson junction. And this energy, I said it comes out to be a Ej 1 minus cos phi. And where this Ej was nothing but simply a I naught and phi naught dash. So this is nothing but this quantity is nothing but the energy stored in the inductor and this term is what is also called the Josephson energy. Sometime we also even call it Josephson coupling energy. And this is what is the potential energy we're talking about. And further, I mentioned that since this EJ is arise due to the overlap. Okay, you can see overlap. So do inductor, insulator, superconductor. So the Cooper pairs are going to move, not tunnel. So this EJ here, remember, this EJ actually arises due to the overlap or coupling of the wave function on either side of the junction. And this is very important to note down here that this the energy shift, that is the EJ, because you look at the equation of U J is nothing but EJ 1 minus cos phi. So this is the just causing energy shift. This is actually simply shift the energy scale. So it is often dropped from the equation. So we can drop it and simply we can say this Uj equal to minus EJ and cos phi. So that equation is the EJ and EJ into cos phi. So this is the offset term. You can just drop it. It's not going to make any change. And this is the, I can say, the potential energy. And since this H cap is now UC plus UJ, and you can see this is equal to minus 4 times EC and del square upon del phi square and minus EJ into cos phi. So this is what where we are now. And of course, you understand now what this EC is. Anybody will tell me what EC is here?
Capacitance energy.
Mm-hmm. That is the charging energy, correct? E square by 2C. So I'm just asking again, because this is a term you have to deal now till end, okay, this charging energy. And now in the system, you can see that if you have some capacitance, okay, for example, if I apply, let us say, so this is the so this is the, let us say, some capacitance C, and this is the Josephson junction, this part. And for this actually for this system, this is the energy Hamiltonian equation for this system. And in this case, this EC will be equal to E square by 2. Now, since this part, look at carefully. So this part actually include one more capacitance inside, that is called the CJ. So technically this C and this CJ, they're going to club together. So this is going to be a summation of C. So in principle, this summation of C is nothing but a C plus CJ. So in this equation, this is how I can define the EC. So you can see that so we have two types of system now. So one is the simple inductor and now one with the Josephson junction. And here in this case, this energy, in our normal LC circuit, which is the inductor and capacitance, you can see that this H is equal to -4 times EC and del square by del phi square minus or plus, that is the phi square by 2L. So you can see that this energy is proportional to phi square, is a parabolic. But in this case, this energy, in our case, this energy is actually a non-linear. It is a cos phi. And if you little bit work on this, so I told you in the last class that this cos phi, nothing but a 1 minus phi square by 2 factorial plus phi 4 by 4 factorial. So you can see that this is actually depends not only on the phi square, but also on the higher order of power. And that makes the potential completely n-harmonic. And as a result, this n-harmonic potential is going to look like this way. And you can see that these energy levels, then they are unequal and the spacing will keep decreasing. And now it become easy for me to access these two states, because if I shine a photon on this, and this corresponds, let us say, H cot omega, then this energy is different from this gap. So only this energy is going to make a transition between 0 to 1 or 1 to 0. It will not going to cause any other transitions. So with a suitable or reliable procedure, I can access the 0 and 1. So I can make the Cooper pair. So that was the part, I think, what we have discussed till now. Okay. So if you or anybody having any question up till here, please let me know. And these equations, these terms, energy terms, we're going to use now. So this is the general situation, general behavior, okay, a general way to make a superconducting loop. And now I will say that this Josephson junction is going to use to create different types of qubits. So either we can make a charge qubit, or we can make, let us say, flux qubit, or we can make a phase qubits. So any different types of qubits we can construct. And in fact, I can say the general superconducting circuit is nothing but this one, that you have a Josephson junction. And this Josephson junction is going to couple with some capacitor. And so in this Josephson junctions, we have a CJ also, and we have a LJ also. And here we have a C. And then we make a normal line here, just one line. And then we're going to have a source here. So this is the ground, and this is another ground. Now it depends, okay? It depends, we can make some changes here, but it depends what kind of qubits you're going to use. So for example, if you have a phase qubit, so in the phase qubit, you're going to have a current source here in the case of a phase qubit. When you go into a flux qubit, so in the flux qubit, it is a little different. So we're going to include one more inductor because we want to loop the flux. So I will discuss separately the flux qubit, and third is the charge qubit. So when you have a charge qubit, so in the charge qubit, you have this system and capacitor and ground here, and then going to put one capacitor here also, and then there will be a source, and that we call as the voltage source, DC power supply, and this also goes to the capacitor, and this is the CJ, and rest remain the same thing. So maybe you can put line here. So this line means on this side, you have a room temperature, and on this side, you have a low temperature. Here also, on this side, you have a room temperature. On this side, you're going to have a low temperature. So this is the typical, I can say, configuration. For the flux qubit, I will draw separately because that required a little bit different approach altogether. Now see, this part, let me highlight. This part is what is known as a Cooper pair box, or sometime we called island. We will talk about. So before we discuss the charge qubit, so now I'm going to discuss in detail the one type of qubit that is called the charge qubit. Now see, in the charge qubit, first of all, I need to understand what is this Cooper pair box. So let us try to first understand this isolated Cooper pair box. So I will draw this separately, this structure, and then we will discuss in detail. So in principle, this include, I mean, here you can see I have included the CG also, half of that part, but at the moment I will ignore that part, and I will just let you know that how this Cooper pair box is going to work here. And this is actually also equivalent to or okay, and of course, always keep in mind that this Josephson junction is actually nothing but this one, that is the CJ. So when I say charge qubit, so superconducting charge qubit, no, which also known as a Cooper pair box. So this consists of a small superconducting island which connect to a reservoir. Through a, or maybe you can just write down that superconducting charge qubit, also known as the Cooper pair box, consists of a small superconducting island connected to a reservoir through a Josephson junction. Which is controlled by, you can see above structure, controlled by gate voltage VG, that is applied through a capacitor CG. And that is the structure already you know here, that how it look like. So what is the CG here, what is VG here, you know. So maybe I will show you some picture. In reality, what is it look like that you have a one reservoir, a big reservoir. It is superconducting material. Then here it is the insulator. And then there is a small box. Okay, so that is the box we're calling. Okay, so the Cooper pair, they're going to tunnel from this to this. So one, you're going to have very big reservoir, superconducting. This is also superconducting, and very small box. No, that box is called the superconducting Cooper pair box. And slowly, you will feel comfortable when I will discuss more and more mathematics. But in principle, this is how it look like. That you have a Josephson junction here in this picture. And in this junction, maybe I can say on this side, you have a reservoir. And on this side, you have that box. This is junction. So this is going to charge, going to flow. Okay. And I will tell you that this is the location finally, which is going to call as the island, where the charges are going to, these Cooper pairs are going to stay. So Actually, what happens that if I, before going into mathematics, if I just tell you basic principle, what happened, just try to understand that some charges, some Cooper pair going to flow, okay, or tunnel from the reservoir side to the box side. And then through this VG supply voltage, we're going to apply some voltage on the capacitor, and then capacitor going to have some charge. Okay. And this charge is going to actually help, okay, help to transfer this qubit. This is going to pull these qubits. So this is going to pull this qubit to the island, okay, or it will push back to the toward this so that they can go back to the reservoir. So the role of this capacitor, the CG capacitor, is to build up some charges. So it will going to accumulate some charges, which I will later on going to call as the NG. So NG is the amount of charges which is going to build up, okay, on the capacitor. And this charge is going to either help to create a Cooper pair on this island, or it going to deplete the number of Cooper pair from this island, depending upon the amount of the positive voltage on the or charge accumulate on the capacitor. So it is going to push or pull. Simply you can understand. It is going to push the charge to the island or pull the charge from the island. So as a result, you will see you will have some N. So N is the excess Cooper pair.
What's the order of this pairing energy between the electrons, please?
Say again.
What is the order of this pairing energy between the Cooper pair of electrons?
Oh, this is in the electron, less than milli-electron volts.
So a very small amount of
Very small
can
amount.
pair.
Yes, exactly. Yeah.
Thanks.
So this N, which I'm calling as the excess Cooper pair, okay. Of course, this excess Cooper pair will be a number, okay. Maybe a 1, 2, 3, whatever you can call, okay. So if let us say if N equal to 1, then I will say key on this island there is a one excess Cooper pair. So one excess Cooper pair. If this is become 0, then I will say 0 excess Cooper pair. I means let us say you can imagine like on a roof, let us say roof is empty and one person climb on the roof, then you will say, okay, one person is there. Okay. If you take him out from the roof, then you can say now number of persons on the roof is 0. So this island, on this island, how many excess Cooper pairs you can create? Okay. So those numbers are there. I mean, so of course, if N become 2, then I will say 2 excess Cooper pair. And understand this N can become -1 also. You understand what is the mean of -1?
Yeah, one less Cooper pair.
One less
Cooper
Cooper
pairs are
pair,
being
exactly.
destroyed.
No, it's not destroyed. Think about like a normal superconductor. And in this, you already have in general, in equilibrium, you have 6 Cooper pairs. Okay. And then what you did, you injected 1 Cooper pair from the outside. Then I will say there is one excess Cooper pair. If I inject 2, then I will say there are 2 excess Cooper pair. And if let us say like this way, then I will say the condition is 0, no excess Cooper pair. And let us say now, if the condition is like this way, that 1 is missing, correct? then I will say n equal to -1.
Sir, it is like electron hole. जब
No, no, it's a
vacant
physical.
space
It is
रह-
a physical qubit coming inside, correct? So
Yes, sir.
it's not a hole here. I'm saying ki there was initially there were total 6 Cooper pairs, and now
Yes.
when there are 6 Cooper pairs, then I will call n equal to 0 state.
Yes,
Normal. There is no excess Cooper pair, so I will say no excess Cooper pair. But if you add one more, then I will call n equal to 1, means there is a one extra Cooper pair. Okay. Or if n
Yes,
equal
sir.
to -1, then you will say, okay, you have taken one Cooper pair out of the system, correct?
Yes, sir.
So this is
And
the
my-
way. I mean, now you can imagine you can make n equal to 2 also, and you can make n equal to -2 also, correct?
Yes, sir. Yes, sir. Thank you, sir.
So it is again like in a room, let us say if there is a family and family members are, let us say, 6. Okay. So this is normal situation. And if I let us say if I introduce one member in the family, okay, then you will say one excess person has come inside the member, correct? Then I will say one excess person is there in the family. And if you take them out, then you will say no extra member in the family. It's normally 6, it's remain the 6. But if you take one out from the 6, then you will say, okay, one member is less from the normal condition. Okay, so then I will call n equal to -1. So this is how you can understand that the
Sir,
number
can I
of
ask one question? Sir,
yes,
these Cooper pairs are bosons, right? You mentioned yesterday.
yes,
So
exactly.
when you have, let's say, 6 Cooper pairs, you mentioned, so it will form as a complete one wave function and act as a one system, right?
Yeah, exactly.
Then from that point of view, how can you use that individual Cooper pair to add and move
Why
from
not? You can definitely add them, right? You can take them out also.
individually?
Individually, yes. I
Okay.
mean, usually means ki you can apply some force and you can just take electron Cooper pair out of that. Okay, like the same way you can think about Bose-Einstein condensate. So if there is a, let us say, 10 number of Cooper pairs in the Bose-Einstein condensate, you can add one more there, right? You can make it 11, 12, 13, 14. The Cooper pair, I mean, there the Bose-Einstein condensate wave function will keep increasing when you start adding the Cooper pairs. So if you can add, you can take it out also.
I think he's confused between the condensate wave function and the wave function of the individual Cooper pairs.
I mean, here, of course, this is going to be they are governed by a single wave function. I agree with that. Okay, but you can add a particle in that cloud. Okay, and if you apply a force, you can just pull one out of them. It is practically done and possible. And don't think that if the Cooper pair are hundreds, you can't change their numbers. Okay, you can't add or you can't take anything out of that.
Okay, sir. So one more
Okay,
thing
good.
about when you illuminate this monochromatic laser source. So in this Cooper pair box, particularly in which point or as a whole you are going to
Well, I'm
apply
not
this?
going to shine any laser here. Okay,
Okay.
just wait. I'm coming to that part. Okay, how
Okay,
we
sure.
will going to work. Okay, so I was discussing this isolated Cooper pair box, and I said that this is nothing but simply this configuration, and already we know that Josephson second equation. If you look at now, so we're going to little bit modify. So see that we have this equation H, that is the Q square upon 2C and minus or plus EJ and 1 minus cos phi. And of course, I said that I can drop one EJ, and this is going to become then EJ cos phi. Look at here. This I also discussed that capital phi equal to phi naught dash into small phi. So it means from this equation, then you can see this is going to become q square upon 2c minus EJ, and cos, this is going to become capital phi upon phi naught dash. Now we're going to do some mathematics. Okay. What I'm going to do, I'm going to write down this Hamiltonian. Now, if you recall a little bit now about the quantum harmonic oscillator, which is nothing but a p square by 2m plus 1 by 2 times kx square. So this whole Hamiltonian is written in this format, 1 by 2 h cut omega. Can you recall? And where this n is called a number operator. And this number operator, how you define? A dagger A, raising and lowering operator. And in the case of a harmonic oscillator, you can see that this A is nothing but m omega upon twice h cut x plus iota p upon m omega. And this A dagger is simply complex conjugate x minus iota p by m omega. So, just I'm giving you some a clue that the mathematics looks more elegant now when you write this Hamiltonian in terms of a number operator. Similar kind of nothing we're going to do here also. So I will recommend you that since this Q is a operator equivalent to a P operator, and phi is also operator equivalent to X operator. And here in this system, you know that the commutation relation of X and Px is how much? Iota h cut. And the same logic you can apply here as well. And you can see that the commutation relation between phi and Q is going to be iota h cut. So these are nothing but a conjugate variables. Same like a X and P. So what I'm trying to do here, this whole mathematics of the superconducting qubit becomes very easy if we work with the number and phase operator. So what I'm going to do now, I'm going to introduce number and a phase operator. So here, this number operator is n cap. The same n which I'm telling you, okay? What is n here? If you talk about number, then n is the excess Cooper pair. But the same thing in the operator form, I can call n cap, and the corresponding even state I can call as the quantum state. And I say this is the eigenstate of n cap, means key n cap when operate on the n, this is going to give a nn. But keep in mind again, this n, and in the harmonic oscillator, for example, in this here, when you go, so this is actually equal to n plus half h cut omega. And here this n takes value 0, 1, 2, 3, and so on. But already I told you here, this n can take value what? 0, plus minus 1, plus minus 2, plus minus 3, and so on. This can go to a plus minus infinity. So in principle, I can say this n is from minus infinity to plus infinity, because this is representing the xx of the xx amount of Cooper pair. I hope are comfortable everybody here up till now.
Yes, sir.
And corresponding, you can see in the harmonic oscillator, this n is also called as the Fock state. Okay. And here we will call this n as the charge qubits now. So these are going to call as the charge qubit. And I know this quantity already because this is equal to what? Minus q upon 2e in number form. But if you write the same in the operator form, this is going to be a 2e. So in principle, I can say this is again equivalent to a p operator. And of course, we already know about this phi. The phi is actually equal to capital phi upon phi naught. So corresponding, I can define a phi operator, which is going to be a capital phi upon phi naught dash. So you have a number operator, you have a phase operator. So we will try to write down this whole Hamiltonian instead of a charge and phase flux. I will write into a number operator and the phase operator form. And you can see even you know that this phi and q, the commutation is iota h cut. Okay, you can try to prove it. No, you take it as homework. Similarly, you can see here the phi cap and the n cap. Now, but it will be simply going to be iota. Okay, again, please try to prove it. So our Hamiltonian is going to become what? Now our Hamiltonian is q square upon 2c minus ej and cos phi upon phi naught dash. And this is going to become equal to, when they put the value, okay, of this quantity. So this is going to become n equal to q by 2e. And from there, I can find the q, that is 2 times n. And that upon c. So this is going to become, okay, बाद में करेंगे, 2 times, this is going to become 2 en whole square by c. And minus ej, of course, this term whole is become a cos phi. So this equation is going to turn further into, let's say 2 into 2, 2 times e upon c into n cap square and minus ej into cos phi. And this I can write also like a ECC into n cap square minus EJ into cos phi. Now see here, this ECC, this is actually not but equal to twice E upon C. And you see, you have another equation called EC. That is a
Right, sir.
it will be a E square. I'm right. Yeah, it will be a E square. 2 times E square. That's correct. And where this EC was equal to E square by 2C. So you can have some similarity between these two. So this is actually equal to 4 times EC also.
4 time ECC. ECC is equal to 4 time of EC.
EC.
That
And this
that
EC
was proved yesterday.
already proved. Okay. So this ECC, I told you that this is actually, if I done the study, then I think already I've given you the definition of ECC also. So this is charging energy for the 1 Cooper pair, correct? So this is the charging energy for 1 Cooper pair, and this is the charging energy for 1 electron. So this already we have taken the equation into consideration. But again, I will like to work only in the EC form. So this is going to become 4 times EC and n cap square minus EJ into cos phi. So you can see that how simple this Hamiltonian becomes, okay, when you write in the number operator. Fine, up till here, no issue. So let's now try to solve a little bit now this equation further. So let's try to find out let's find the matrix element, because I want to find the energy eigenvalue. So once I find the matrix element, then I can simply solve the Schrodinger equation. Solve Schrodinger equation and I can find the energy eigenvalue. So matrix element, all I hope you are aware how to write down. So the matrix element will be HMN. And this is how I can write. So if you put here, so this N and M, of course, they are the same. They are the index, I can say, from the same set. So you have a set of eigenstates, and out of those, M is also equal N out of that number, but we can make a condition that M equal to N or not equal to 1. So now if I put here this value of H from this equation, so this is going to become 4 times EC and M and N cap square and N minus. Okay, before going to this now, let me, because it will become difficult to solve this cos phi in this format, but this cos phi, I can write also like a e power iota phi plus e power minus iota phi divided by 2. So you can see this equation is become much easier for us to solve. So this is going to become EJ by 2 and e power I phi and plus e power minus I phi. And now I can find out the matrix element. So you can see this HMN is going to become M and HN, and this is going to become 4 times EC, M and N square into N and minus EJ by 2. And look at here. So this is going to become M and e power iota phi into N and plus again m and e power minus iota phi into n. And maybe you can prove that e power iota phi, when going to operate on the n, you will going to get n plus 1. It's like a raising operator. And when e power minus I phi operates on n, this is going to n minus 1. They are like raising operator and lowering operator. But raising and lowering what? Raising what they are raising? They're increasing the number of, tell me, Cooper pairs. So I think it is better to always use the word excess, because n is not only the number of Cooper, this is the excess Cooper pair. So extra Cooper pairs. So that is the equation here. So now you can see the first term. This first term is what? 4 times EC m and n square n. This is actually become 4 times EC. Now, since this n is the eigenstate of n square, n, so this is simply become n square and mn. And this is nothing but a 4 times EC and n square and delta mn, delta function. And this is actually equal to 4 times EC n square if m equal to n, or equal to 0 if m not equal to n. So these are the simple mathematics. And what about second term? That is the m and e power I phi and n. This is going to make m and n plus 1. So this is a delta m and n plus 1. And you can say this is going to be equal to 1 if m equal to n plus 1. And this is going to 0 if m not equal to n minus 1. And the third term simply, similarly, e power minus iota phi n and m n minus 1, delta m n minus 1. And this is again equal to 1 if m n minus 1 and equal to 0 if m not equal to n minus 1. So when you're going to write down the matrix, how it will look like? So if you write down the matrix for, let us say, the first term for this one, so you can see that this is going to be 4 times EC. Remember, the n can take value 0, plus minus 1, plus minus 2 to plus minus infinity. So the matrix you're going to get, it is going to infinite matrix, okay? So it will go from plus infinity to minus infinity. Oh, sorry, it will be like that. It will be a minus infinity to plus infinity. And look at here, these diagonal elements, only they will be non-zero in this case. Because if m equal to n, then only this term will be non-zero and rest will be 0, 0, correct? I'm not going to write down any matrix here, but I'm just trying to tell you how it will look like. Or in this case, you can see that here, this just one below the diagonal element will be non-zero. And in this case, one above the diagonal will be non-zero. So just you try to figure out yourself. I'm not going to write down these matrices here. Better we can focus on the calculation part. But overall, this H Hamiltonian, in this case, when you write down, so including the matrix element, so this H is simply going to become that matrix element HMN, of course, into MN. So this is how I can write down the Hamiltonian. And of course, here will be one will be m, other will be n. And this is nothing but equal to HMN, nothing but m and HN. So into MN. And now if you put the value, okay, so this is going to become look at here. Because now I'm going to put the value of m, and in this case, this m is already I've taken care in equal to n or n plus 1 or n minus 1. So the summation will not go with n, but only with the n only. And this is going to become 4 times EC n square and n. Okay, you can see that for the first one, this is going to be non-zero only when m equal to n. So I have taken care here. And then minus in the second part, this is going to be a EJ by 2. And here you can see one will be this and this. So one n plus 1, another will be n minus 1. So this is going to be a n plus 1 and n. And second will be a n minus 1 and n. So this is the Hamiltonian in the number operator form. I have completely written the Hamiltonian in the number form. Or you can say this is the Hamiltonian in the number basis. And now from here onward, I'm going to make our life simple. So we go only for a 2-level system. 2-level system means only n0 and n equal to 1. So when I say n0 means 0 xs Cooper pair and 1 xs Cooper pair. So 0 xs and 1 xs Cooper pair tunneling, okay, through Josephson junction. So only these two numbers I will take. Rest I can ignore, no, because n go from minus infinity to plus infinity, and here this h become then very simple. You can see here. So if I put the value, so look at here, this n, I will put first 0. So this is going to become 4 times EC, and 0 means 0 square and 0 and minus EJ by 2 and 0 plus 1. That is 1, correct? And 0, and this become minus 1 and 0. That is the for n equal to 0. So this is whole is for n equal to 0, and plus for n equal to 1. That is going to be 4 times EC and 1 whole square and 1 and minus EG by 2. And here it will be a what? 1 plus 1, 2, and 1 here plus 1 minus 1, 0 and 1. So this is for n equal to 1. Now see, since we are taking only n0 and n1, so these states will not exist. So it means there we're not taking this part into account. So you can see that this section will be 0. This will be there. This will be there. Now look at, we are not taking the minus 1. So this also going to be a 0. So finally, this energy become what? This already part gone to 0. So this become 4 time, let's say EC, and 1 and minus, look at here, the one term from this side and one term from this side. Okay, so I will take EJ by 2 common out, and it is going to become 1, 0, and plus 0 and 1. So for a 2-level system, this is the Hamiltonian you have. Now, if you define 0 as a 1, 0 and 1 as a 0, 1, then the outer product of 1 and 1, it become what? It becomes 0, 1 and 0, 1. So that is going to be a 0, 0 and 0, 1. Similarly, you can see 0 into 1 means 1, 0 and 0, 1. That is going to become again 0, 1, 0, 0. And same thing I can write for this also. So look at here. This Hamiltonian in term of matrix, this has become 4 time EC 0, 0, 0, 1 minus EJ by 2 into 0, 0, 1, 0 and plus 0, 1, 0, 0. I can just add these numbers and you can see you're going to have a 0, 0, 0, 4 time EC. And this is 1, 1. So this is going to become 0 and EJ by 2 and also EJ by 2 and 0. And from there, this H cap then simply become 0 and minus EJ by 2 and minus EJ by 2 and what? 4 time EC. So look at, this is the matrix you are getting, okay, for an isolated box, okay. So we have developed the Hamiltonian, a quantized version of the Cooper pair box. So as a Cooper pair box means nothing but just a capacitor and inductor. So this is the quantized Hamiltonian for Cooper pair box. Cooper pair box, nothing but again this. So we know the Hamiltonian for the Cooper pair box. Now let us try to make the complete circuit. Now again, let's come back to our circuit which I had drawn earlier. So we have a Cooper pair box here. And then one extra capacitor. And this goes to ground. And I said that key we're going to apply one capacitor here that I can call as the CG, and then one power supply that is called VG, and this also grounded. So maybe you can write like a Cooper pair box to an voltage source. So now we are trying to understand how everything works here. Okay. So keep in mind that this part is the Cooper pair box for which already we have found out the Hamiltonian. Now see what's going to happen here. When you apply some voltage, so maybe you can write down better. The voltage which I call VG, which is DC in nature, doesn't inject current because this is a DC voltage and you have a capacitor here, okay? So this capacitor will not allow the DC current to pass through. But it induces an electric field which leads to polarization of a capacitor, that is the CG. And once the capacitor get polarized, okay, this will push or pull Cooper pairs on the island. And here is the island. I can just call this is the island. So this is going to cause no, it will going to pull some or push some no Cooper pair on the island. And how it does, okay, so there is a term I'm going to define here. Let us see, already you know this N is nothing but a excess Cooper pair on the island. Or you can say number of excess Cooper pair on the island. And I'm going to, and this of course, N is 0, plus minus 1, plus minus 2, so on. Now I'm going to define NG. And very careful. This is the induced effective charge due to the gate capacitance or capacitor and VG. So again, I'm repeating. So when you're going to apply VG, what will happen? This VG applied across the CJ, that is the capacitor, that is called the gate capacitor, and it going to create electric field here. I mean, so maybe this side become positive, this side become negative, or vice versa, depend upon what type of polarity you're going to put here. So it is going to create electric field. Electric field may be in this direction or maybe in this direction. And doesn't matter what is there, okay? So once, let us say you have positive charge here. So if this side is positive, then this also going to create electric field on this side. So you can see that this electric field or charging of the capacitor is going to create electric field between gate electrode and superconducting island. So please mark this line, okay, that this charging capacitor is going to create electric field between this electrode and the island. And this electric field is induce a charge or going to induce charge polarization on the island. So I think better, I think you can write down, then you will remember for a long time that electric charge, this CG or charged CG creates electric field between gate electrode and island. Further, one more point you can write down. This field induce a charge polarization on the island, effectively pulling positive or or you can say pulling, better word, pulling Cooper pairs, pulling XX Cooper pair on the island, or pushing Cooper pair away from island. All right. And and this is done by this Ng, no? Because this Ng is the amount of effective charge induced on the capacitor. As a result, the charging energy of the island. Now this will going to be a, let's say, called E charging. This is going to be 4 times EC. It's not only N square, but N minus Ng whole square. So this N going to be subtracted from the Ng. So this is the difference you're going to see here. This is going to cause this charging energy is going to be a 4 EC. I mean, earlier, look at in the Hamiltonian, when you write down this Hamiltonian. So in this case, the Hamiltonian going to change completely. So when you solve, I'm avoiding lots of mathematics here. I'm just trying to go through some logics only. So when you write down the Hamiltonian, when the system is attached with the VG, so in that case, the Hamiltonian is going to become 4 times EC and N minus Ng whole square and minus EJ and cos phi. So this is the Hamiltonian for this system. You must also keep in mind that when we were working for the only normal system, then we had this Hamiltonian. Only 4 times EC N square minus EJ cos phi. When the Cooper box was not attached to the VG. So here you can see the VG equal to 0. So Ng also equal to 0. But you can see that in this equation, then when you attach with the VG and CG, then you're going to have this equation. And that turns out to be same. When the VG becomes 0, this Ng also becomes 0. And then Hamiltonian simply become 4 times EC and N square minus EJ into cos phi. Is this clear up till here? Then rest will be very simple. Look at here. If you recall here, what I did, I wrote down this Hamiltonian for the system when the VG was not there. And then I solved the matrix element by this method. and I calculated the matrix of the Hamiltonian. The same procedure I will do here also. I have now this Hamiltonian, okay? I will find the matrix element, but I will not do the mathematics now. You can do yourself. So the matrix element, when you do, I mean, so you can try to find out the H cap Mn, okay? The same logic, no, what we had. And you can do the same calculations here. And finally, we're going to get this Hamiltonian. That is the 4 time EC and Ng square and minus EJ by 2 and minus EJ by 2. And here it will be a 4 time EC and 1 minus Ng whole square. And you can see that when this is the situation when the Vg Ng 0, then the same Hamiltonian, nothing but a 4 time 0 and minus Ej by 2 and minus Ej by 2, and this is going to be a 4 time EC. And now with the applied voltage, this is the how it's going to look like. Now, one more step I can do here. That is called to make this Hamiltonian symmetric in nature. And from here, now what I can do, even I can introduce ECC, that is the 4 time EC. Then in that situation, the Hamiltonian is going to become ECC and Ng square and minus Ej by 2. So what I can do, I can try to create a symmetric form of the Hamiltonian. The diagonal elements are not symmetric, okay? They should be symmetric in this case, and this is very simple. For example, look at if you have a number like -1, 0, +1, +2, +3. This is not symmetric. So what I can do, I can just shift 1, okay? So I can simply add or subtract -1. So this will become -2, -1, 0, and +1 and +2. Now you can see around 0, the system becomes symmetric. The same thing I can do here also. So I can make this system symmetric. And to make the system symmetric, what I can do, let's just make this term as a E0 and this term as a E1. And I can define a term called E average, that is equal to E0 plus E1 by 2. And I can simply find the symmetric Hamiltonian, and I can say H minus E average into I. And you can do yourself all these parts. And you will get this equation minus ECC and 1 by 2 minus Ng and minus Eg by 2 and again minus Ej by 2 and ECC and 1 by 2 minus Ng. So you can see that the Hamiltonian becomes symmetric.
Sir, the fourth term, which is in Hamiltonian, 4 EC minus into 1 minus Ng whole square. Is it
Mhm.
whole square or 1 minus Ng square?
Sorry, Ng square.
Okay.
So this is terms you have now. And what I can do, I can again introduce another term. Let's say put E equal to EC and 1 by 2 minus Ng. So this Hamiltonian further becomes simple. It is 1 by 2 and minus E and minus no, not like this. Not like this, please. I can define E as a ECC and 1 minus 2 Ng. So in that situation, this H cap is going to become 1 by 2 and it become minus E minus EJ and also minus EJ and E. So we are almost done and we are going to conclude now, and we will see how this superconducting system going to act like a qubit. But keep in mind, this E is very important term again coming here. Now, this is actually which you have defined here. This you can also define like a E1 minus E naught, which is nothing but actually equal to ECC and 1 minus 2 Ng. So this is nothing but a energy difference between 1 and 0 state. So this is the energy difference between the 0 and 1 state.
Sir, the Hamiltonian we have derived or used better. That is for two-level system, 0 and 1, right?
2-level system, exactly. It is
Okay.
for 2-level system. Yes, that's
Okay.
correct.
And then when we talk about the value of Ng, what it could have been the value of more than 1 also, 0, 1. apart
Exactly.
from-
That's true.
Okay.
That's
Okay,
that's
fine.
true. Keep in mind this N is here in this case is 0 and 1, correct? In this case,
Yes,
but this
because the
Ng,
Hamiltonian used
yeah,
that is
but
for
this
two
Ng,
levels.
remember, this is a charge induced, it is induced, no? So this is continuous, okay? It's a continuous quantity. It can be fractional also. Now, let's come back to this equation further.
So-
So you have this one.
Sorry to disturb again. So this about this fraction. Could you please explain how it super pair displacement will be fraction?
Say again.
The value of this Ng could
See
be
what I'm
fraction
saying.
also, right?
See, this is look at the induced gate charge, right? So how many charge are induced, correct? So let me call that as the QG on the CG. This is equal to how much? This is going to be a CG into VG, correct? Agree, I'm right? On the capacitor that is called CG. If we apply a voltage of VG, then how much charge will develop? This much now. And this QG is also equal to let's say Ng into 2E, correct? So you can see that this Ng from this equation is comes out to be a Cg and Vg upon 2E. So that is the expression for the Ng. So this can take any value. Remember that this is not a Cooper pair. This Ng is not a Cooper pair, okay? This is just a charge induced, okay, on the surface of the capacitor, okay? So Ng is not actual number of Cooper pairs. It is a dimensionless continuous parameter. It can take any values. If I say Ng is like 0.3, 0.5, 0.75, or anything else. keep in mind that this is not a count of Cooper pair. It is a way of expressing, okay? This Ng is simply a way of expressing the induced gate charge in unit of Cooper pair. So I think I must clarify further. This Ng, how you can say, is a way of expressing the induced charge in units of Cooper pair charge. So keep in mind that this capacitor, which is equal CG and attached with the VG, this gate capacitor and the voltage, they don't going to inject any real Cooper pair. Okay, they are not injecting any Cooper pair. This is just charges are going to accumulate on the surface. They induce electrostatic energy bias. Are you getting this word? So when you're going to connect this power supply, okay, with a capacitor, and this is also connected with our island. Then this is going to induce charge QG this much. So this much charge is going to induce. And the number of the such charges are going to be 2E. That's the reason I'm telling you this is in term of a unit of a Cooper pair charge. So you can divide this 2E and then you can find this Ng in this number. So even if you see, look at here, even if the QG is become E, correct? You can see the number of charge on the surface of the plate is E. Then tell me what is the value of EG? Ng? And you can take, let us say, VG some number 1. So Ng
That will
become
be
how much?
half, right?
Is a half already, so you can see. So since you are defining in term of a unit of Cooper pair charges, so this number can be anything. So this can be a fractional number. So half a Cooper pair. But it's not a Cooper pair actually. It's not really a half Cooper pair. Okay, so keep in mind this Ng is not a Cooper pair. This is just an induced charge which is expressed in units of Cooper pair charge, and this number can be anything. So again, please keep in mind this N is the number of Cooper pairs, number of excess Cooper pairs, but this Ng is simply a gate induced charge. This can be a fractional. Are you getting or? Okay, you think about now, I can give one analogy to understand, okay? Some another way to think about river and the lock gate, okay? And imagine Cooper pair is like a water molecules. And the lock gate, which is stopping the water flow, okay, is like a Josephson junction. And then you have pressure control, that is the gate voltage. So if you don't actually open the gate, but by raising the pressure, I mean increasing the VG. So you can increase the VG, you can create a tendency for more water to flow if the gate through the gate, correct? So that pressure bias is Ng. That pressure bias is Ng. Is not real water, but a potential to move the water, okay, through the gate. So keep in mind this Ng is a continuous because Vg is continuous, okay? It is just acting like a knob that tune the energy levels of the charge state. So when the voltage increases, so the Ng will increase and that is going to push some charges there. If the voltage goes down, Ng will go down and there will decrease the number of Cooper pairs there. So this is how I can simply express this Ng. All right, shall we go ahead? So coming back to our mathematics. So I said this Hamiltonian is actually equal to what? 1 by 2 and minus E and minus EJ and minus EJ and E. See, I can write this in this format, and that is the whole mathematics you're going to understand here of the qubit. This is equal to 0, 1, 1, 0 and minus E by 2, 1, 0, 0 minus 1. I hope no problem if I write in this format. And can you tell me what this quantity is? Anyone? This matrix is
Sigma X.
Sigma X.
Sigma Z.
And this matrix is
Sigma
Sigma
Z.
Z. And
Sigma Z.
yes, and that makes the whole thing interesting. Look at here. This is going to become minus EJ by 2 sigma X minus E by 2 and sigma Z. Or I can write in this format also, H cap equal to minus 1 by 2 column matrix, row matrix, sigma X and sigma Y and sigma Z, and one column that is the EJ, 0 and E. And what is this? It is a sigma. And if I call this quantity as some, let us say BE, then this whole equation is actually equal to minus 1 by 2 times sigma dot BE. So this is the Hamiltonian for the charge qubit. And look at, if I write down for the spin qubit, so for spin qubit, how we write down? Minus gamma and H cut by 2 and sigma dot B. This is for spin qubit, which we discussed, for example, electron spin. So you can see here that this charge qubit is the Hamiltonian is exactly similar like a spin qubit. The only difference that this BE here, this BE is not magnetic field. Whereas in the case of spin qubit, this is a real magnetic field. But this is behaving like a magnetic field. So this BE is actually equal to gamma H cut into B. And we call this as the fake or fictitious. It is playing a role of magnetic field, but is not a magnetic field. And because of this similarity between this, you can see that the spin qubit equation becomes charge qubit equation. So you can apply whole mathematics of a spin qubit on the charge qubit. So a Cooper pair box qubit is simply behaving like a positive charge spin qubit. This is going to behave like a charge qubit, and all our mathematics what we have done till date from the spin qubit. So for example, the blosphere, here also try to understand this BE, which is actually equal to EJ0 and E. And if you look at the BE magnitude, this is actually equal to EJ square and E square. In principle, this BE nothing but a EJ x cap plus E y cap. So this EJ BE lies in XY plane. Now onward, I'm going to call this as a magnetic field, but always keep in mind, this is not a magnetic field. So this is actually lies in the XY plane. So here you can think this is the Y and this is Z and this is the X. And this magnetic field, the magnetic field I can show like this way. This is the BE. And its component along the x-axis is what is called EJ, and its component along the ZX along the sorry, not I made a mistake. It will lie along Z-axis. So in the XZ plane. So please correct it. It is because it is only X, Y is 0 and Z is there. Okay. So along the Z-axis, the component is actually a E. So this much component is E and this much component is EJ. And this is actually behaving like a magnetic field. And here you can see that I can call this as a 0, technically n equal to 0. So 0 XX Cooper pair. Here I can talk about 1, mean n equal to 1. That is the 1 XS Cooper pair. Here and here we can call about plus and minus. So this is the blosphere for charge qubit. So whole mathematics of the qubit is applied in this case. Any question anybody want to ask up till here? Hmm? So rest is simple. I mean, you can construct your qubits. You can apply this VG is going to control n. Okay. So by changing VG, you can make n equal to 0. By changing VG, you can make n equal to 1. Means you create a state called 0, you can create a state called 1. So you can see this VG helps actually creates qubits like 0 and 1. Now question that key, what we want a superposition state. Means I want a state called plus √2 and 0 and 1 and so on. I want to create this state. So how I can change the VG so that this state can be created? So something in the superconducting qubits, something will called a sweet spot. Very popular. So we say charge qubit at its sweet spot. Now see, this Ng is equal to Cg Vg upon twice E. And look at, if I change the voltage in such a way that this Ng becomes equal to 1/2. And this is possible, very easily possible, that I can just take Vg equal to how much? E by Cg. So if I put the voltage this much, then I can create number of charges equal to half only. And in this situation, look at a very important parameter called E. Can somebody tell me what E was? ECC and 1 minus 2 Ng. And what this represent? Hmm? One. And in this situation, you can see the E become what? 0. If E becomes 0, then look at the Hamiltonian. H dash, that is 1/2. That was a minus E and minus Ej and again minus Ej and E. So this is going to become 1/2, 0, minus Ej and minus Ej and 0. This is simply equal to minus Ej/2, 0, 1, 1, 0. Now tell me what this matrix is. Sigma x. So this is nothing but a minus Ej/2 into sigma x. It means in this situation, the PE. So you can see that I can write this way also, minus 1/2 and sigma x, sigma y, sigma z, and this matrix is become Ej 0. This is what is called the sigma dot BE. So you can see that the BE simply becomes what? Ej into x cap. Agree, everybody? It means in this case, this if I define This is the y-axis, this is z-axis, and this is the x-axis. Then in this case, the magnetic field, okay, that fake magnetic field that is called the BE, it is only along the x-axis. All right. And in this situation, it can be like this way or other way around, minus भी हो सकता है. So in this case, then the eigenstate, you can solve this eigen matrix and find the eigenstate. The eigenstate of H dash will be plus and minus. So here you can see that when this BE along this direction, then only plus and minus will be the eigenstates. It means you have created a superposition state, because plus nothing but a 1 by root 2 0 plus 1, or minus 1 by root 0 minus 1. So by changing the voltage equal to E upon Cg, you have created Ng equal to half. And in this case, the situation is like that way, is like that on the, this is the capacitor here, and this is the Josephson junction, and that capacitor another here. And on this island, the charge here is half, and this is such that the situation is like that on the island there will be a Cooper pair or there will not be a Cooper pair. It is a superposition state. There is a possibility that there will be a Cooper pair and no Cooper pair. Okay, both going to exist at the same time. As a result, here either you will be in this state or in this state. So it is a excess of a Cooper pair. If there, then you are in the state in the state 1. If no, then you are in this state. If half possibility, so this is a situation when the Ng equal to 1. This is situation when Ng equal to 0. Okay, and this is situation when the Vg equal to is twice of E upon Cg. And in this case, Vg equal to 0. And this is the state you're going to get when the Ng equal to half. And this is the case when Vg equal to E by Cg. You can see that. This is the how you can create a quantum bits. Comfortable, everybody? I can understand this is a task or not so easy sometimes because of lots of mathematics. But at the end, I think you understood that this excess of Cooper pairs or no Cooper pairs, okay, they actually going to act like a 0, 1. And why they're going to act like a 0, 1? Because this whole Hamiltonian, okay, is actually resembling with the Hamiltonian for the spin qubit. And that makes this whole situation similar like a spin qubit. So, any question? And only one thing is left. Now see, with the changing Vg, you can create state 1, state 0, or state plus, or any other superposition state. Okay. But once the Vg is set, you will be only in a one state. So remember, last point, once VG is set, then state is also fixed. Is also fixed. Then how to change the state then? Okay. Now to change the state, what you do, we apply RF field or microwave, actually. Microwave field externally. So what we do, this is the last point, no need to do any mathematics, although mathematics is there. So there's a capacitor here. And then you have this, our Cooper pair box. And then there is a VG. And what we do here, we're going to superimpose, okay, RF field also along with that. So this VG will be equal to VG plus some VRF, okay. So we're going to apply RF field along with that. Now this RF field, what it will does, okay, it going to do, it will going to increase, I mean, in the positive cycle, negative cycle, you can see here, depending positive negative cycle, it is going to change the potential, okay, here, no, number of charges on the capacitor. So number of charges on the capacitor will keep go up and down, okay. Or in other words, you can say that this will going to change the potential of island. So potential will increase, decrease, and accordingly the number of Cooper pair, they're going to increase or decrease, okay. So by shining the number of this microwave, actually we can push more number of Cooper pair, or we can pull number of Cooper pairs, okay. And this is done by this RF. So finally in the superconducting qubits, you set the voltage, you create qubits, and after that everything is paid by this RF voltage. And this RF voltage is nothing but the separation between this state 0 and 1. So this separation is h cut omega, let us say R. So whatever RF you use, this VRF, that is a V naught into sine omega RF T upon phi. So this is the applied RF voltage you produce, so that your system, and the system you can actually manipulate, okay. So you can create a superposition, you can create a gate, whatever. I mean, so in the spin qubit, I mentioned you that I can apply RF and we can do anything. You can create a NOT gate, you can create a Y gate, X gate, Y gate, Z gate, C naught gate. All those things you can do with the RF here. So that's all from my side for the. Oh, screen is gone. Okay. Any question anybody want to ask?
Yeah, hello, Sugam.
Yes.
Yeah, so we have drawn a parallel between the position momentum and the charge and the phi, right? So far, I
Yes.
think
Yes, that's
looking
true.
at the Hamiltonian.
Exactly. Exactly.
Yeah.
Yes.
So how far we can extrapolate it, even for even operator formalism we have extrapolated.
Yes, you can extrapolate to almost every part. Okay, you can write the raising operator, loading operator in term of Q and phi.
So in between you have used e to the power I phi as the raising operator, but then right, e to the power I phi.
It's not a raising operator. It acts like a raising operator, but it's not a raising operator. Raising operator will be different altogether.
But in this formalism, raising operator is also increasing the number, right?
Exactly, with some value at the output. Okay.
Right. So that's not similar to the raising operator.
No. I mean, this e power I phi, this act like a raising operator, but it's not a raising operator. Okay.
Yeah, I had a
Raising operator will be,
confusion.
of course, a dagger.
Yeah.
n, this is going to cause some c plus and n plus.
Because dagger A, in this case, if you apply, it will be 1, e to the power I5 and e to the power minus I5. So, yeah,
Whereas this n is always going to be a dagger A, correct?
correct.
Yeah.
Yeah,
So this is not a raising operator. I said that it is behave like a raising operator because
I
it's just
see.
changing the eigenstate, but this is not a raising operator.
Okay. Yeah, as far as the parallel concerned, again, what about uncertainty? Can we extrapolate?
Yes, exactly. You can extrapolate this.
Okay, yeah.
Everything you can extrapolate the same. Because see, in the quantum mechanics now, when we talk about a system and the wave function, so wave functions are not real.
Right.
So it's not something that something is oscillating, and we call that as the some wave function here. So wave function is still a mysterious quantity for us. So in this case, for example, electron, let us say, when you talk about electron spin, so till date we don't know exactly what is the wave function of electron spin. We still deal it with the mathematically as a just as a matrix. For example, you think about orbital angular momentum. You have the functional form of the L, but there is no functional form of the spin state.
All right.
So these wave functions are not now physical. So when you start making analogy that there is a position, there is a momentum, then there is a charge, then there is a phi. Okay. So how far we can go together? You can go in the quantum mechanics as far as you want to go. They are going to behave similarly. The wave functions going to behave. I mean, there are different quantities in this case, but they're going to, you can treat them in a similar way.
Were there criticism for this treatment earlier? I mean,
Which,
for the mathematics, were there the criticism for this mathematics?
no, I'm not getting.
No, criticism. Were there? So the parallel that we are drawing, were there criticism? Were there a lot of criticisms for this?
I mean, so again, my observation or my point is that there's no meaning of creating criticism on the analogy, okay, and the similarity, because till the day you don't know the physical interpretation of psi, okay, there's no meaning of even doing criticism.
Yeah.
Just if we know the true meaning of wave function, then one can definitely criticize. Oh, you cannot make an analogy. You can't equate q versus position and momentum and phi versus position. But this is the open situation. You don't know exactly what is the meaning of wave function there. Okay, so doesn't matter. You can make a parallel.
Yeah. Right.
And there's no, I mean, there's no ground of creating criticism here.
Right. Yeah. Thank you. Yeah.
So we can see that here we can easily think about electron Cooper pair, excess of electron Cooper pair. So this is actually act like a state. Now, so this is a very important argument somehow giving. So you can consider any thing like I told you in the day one class, coin having head and tail. So if this head and tail, of course, this coin cannot act like a quantum system. I cannot make head as the cat and bra is counterpart. Okay. Because the coin not going to act like quantum mechanical particle. Okay. This is because a big system. Okay. But this gives you analogy that if the system is quantum mechanical, so even if the coin is a quantum mechanical, then I can consider this head and tail as the two quantum states like 0 and 1. Because nothing is physical here. So even you can think like if there is some situation where the let's say two mountains, okay, one mountain higher, one mountain lower. So height of these two mountains, if this is still remains quantized, okay, you can consider this height and this height as two quantum state, 0 and 1. So any analogy Now you can create, if the system is a quantum system, then you can make those system, you can treat those system as a quantum states. And this is the where the this topology, quantum computing comes into picture. So you can think any kind of quantum system, and if you have the idea, okay, this can have a discreteness. So discreteness of the shape, discreteness of the charge, discreteness of the numbers, discreteness of the potential height, then these discrete systems can be treated as a quantum state. They can be treated like a 0 and 1. I hope I'm able to convey the masses. Is it?
Yes, yes, it is clear. Yeah.
So even it's still open field. You can still think, anybody can still think that what different kind of quantum computer can be made out of. It's not always about the superconducting qubits where the numbers, we're talking about numbers. Okay, so 0 number or 1 number. So Cooper pairs is there or not there. This can be. Now, based upon the same logic, you can think in the superconducting system, the thing about the flux. I told you of flux quantization. So flux is quantized. So if something is quantized, okay, doesn't matter what it is a flux quantized. So this quantized flux, so two states, okay, two flux values can be used as a 0 and 1. Phase also is a quantized quantity here. It can be also used as the two levels, 0 and 1 in the quantum, in the superconducting field itself. So in the superconducting field itself, you can see there are three quantized things. One is the number of Cooper pairs. One is the flux. Other is the phase. In the case of, you can talk about electrons. Of course, in the case of electrons, spin, we have only spin up and spin down. In the case of hydrogen or any atomic system, so these energy levels are discrete. But you have multiple levels. So these discrete levels can be used as the quantum bits, 0 and 1. But of course, you can have a
sorry,
0, 1, 2, 3, 4. But the good thing here is that these 0, 1, 2, 3, they have a different spacing.
what
Only
time do
problem is
we-
that we don't want equally spaced lines. Yes, Gagandeep.
Yeah, Professor, what time do we meet tomorrow?
6 o'clock.
Okay, great. Thank you.
So
Sir, whether there will be another quiz tomorrow?
you want, then I can held, or I think I prefer to held on Sunday.
Sunday. Okay,
Yeah.
okay. Okay.
So tomorrow, let me finish this iron trap part, and then we can have one quiz. Okay, on Sunday maybe.
So as planned, Sunday we have Q skit also, right?
Yes.
Do we have time for that? Yeah.
Yes. 30
Yeah.
minutes for the quiz, and then remaining time we can go for the biscuit.
Okay.
So please think on this quantum computing part. Maybe you can come up with a different idea completely. Maybe you can find a different system altogether, which actually going to provide you a new set of quantum states, which are more robust. In the case of, you can think like photons also, these polarizations can be used. Okay, just try to think. I mean, maybe you can come up with a new idea altogether. I will also talk maybe tomorrow about some more quantum system. There's a company called D Wave, okay, and they are using completely different mechanism. annealing mechanism to create the quantum states. So maybe we can talk maybe tomorrow a little bit about those also. So idea of this here is that if by after taking these classes, if we can not only stick to the mathematics, but if we can become a little bit more innovative and try to think that there's a possibility to create even or find a new quantum states or new system which may not require cooling at all. For example, in these systems, we need a cooling. Maybe you can find a new quantum systems which can act like a 0 and 1, and you can create gates using that, but that doesn't need any cooling and very good amount of coherence time. Then that purpose of this school is fulfilled. So we just need to little bit become more creative on this aspect. We should not stick to the just existing platform, existing systems, which are all which we are studying. We can think out of box, and we can even find a new quantum systems which can act like a qubits. That's all I think from my side for today, and remaining we can discuss tomorrow then.
Yeah, I don't see Sunil here. Maybe
Yeah,
we can
so I
wind up.
think we can stop it. Yeah.
Yeah,